Good morning, everyone. Welcome to the 8th and last session for the virtual International Forum on Tuberculosis 2021. Want to remind all the speakers and attendees that this session is being recorded and streamlined on Zoom and simultaneously on Facebook, YouTube, and the Imagen TV UBC channel. And also we have translation interpretation services, both English and Spanish. For further information, you can check www.remittv.org. This event is done with the support of the Center of Audiovisual Resources from UBC Department. Want to thank all of you for your great work. This forum is taking place thanks to the support from different institutions. Health Science School through the internalization program by the UABC. Border Health Commission, Mexico and US. Binational Thematic Network and Multidisciplinary Research on Tuberculosis, REMIT-TB. National Center for Preventive and Control of Disease, CENAPRECE, by the Ministry of Health in Mexico, and also the National Network for Research for Prevention and Control of TB in Mexico. It's important to highlight that the purpose of this forum is to generate a good channel of communication for access to science at the international level regarding the prevention, diagnosis, and treatment of TB under the new framework of COVID-19. In this way, you should be ready to prepare yourself for future possible pandemics. And we remind everyone that we're gonna issue some proof of attendees if you have been here for at least 6 sessions. After the end of each session, you have to register through the QR code, which will be forecasted during the session. Today, we have the participation of 2 great speakers, Dr. Pierre Baldi and Dr. Shizem King. Each talk is gonna last 45 minutes and from 5 to 10 minutes for Q&A. And the speakers, we're gonna thank you for if you speak slowly because we're having simultaneous interpretation at the same time. So we're gonna start today's session with the participation from Professor Pierre Baldi, who is a distinguished professor at the Science Communication Faculty at the California University, Irvine. He courses in artificial intelligence and e-learning, especially emphasizing deep learning, neuronal networks, and their the theoretical applications. Applications, particularly in neuronal sciences, physics, high energy physics, chemistry, prediction of chemical reactions, discovery of drugs, and chemoinformatics. Genetic regulations, omic sciences, prediction of protein structure, bioinformatics, and systems information biology. Among the different awards he has been granted, New Orleans Research Award, Faculty Innovation Award, Microsoft Research Award. The title for this first presentation is Artificial Intelligence and Biomedical Imaging. Thank you, Professor. Thank you so much.
Muchas gracias, Professor Vargas. Thank you, everyone, for inviting me. It's a pleasure to be able to talk to you today. My talk is not focused on tuberculosis per se, but it's a broader talk on AI and in particular deep learning methods, which is neural networks, applied to image analysis, to computer vision, and in particular to images or videos that are produced in the biomedical sciences, which of course is very relevant for tuberculosis. I recently published a book with Cambridge University Press that contains a lot of the theory behind what I'm going to present and a lot of the references. So if anyone is interested, you can take a look at the book. There are chapters that are available for free on my website if you're interested. And one key point I want to make between the relationship between AI, deep learning, and biology is that it's a two-way relationship. Of course, we use deep learning in applications, for instance, applications to biomedical imaging, but in the other direction, all the ideas about deep learning and neural networks are really inspired from biology and from neuroscience. So this is what I'm going to try to show you from an historical perspective. Deep learning really started in around 1950, when people started thinking about the brain, how it works, and how we can try to build artificial systems that are inspired by the brain. So if you look at what scientists knew around 1950, well, you know, on this slide, you can see in the upper left, you have Darwin. So they knew the brain is the product of evolution. They knew that the brain has a specialized area. This is Broca, Charcot, the Wernicke. There are different scientists that discover different areas in the brain that are specialized for speech, for instance, or for vision. They knew about the anatomy, Ramon y Cajal in the upper right. So they knew about neurons, pyramidal cells in the cortex, and so forth. They knew about synapses. This is Sherrington. And through the work of these two gentlemen here, they knew that neurons are communicating using very tiny electrical signals. On the theory side, you had things like Turing machine had been developed by, the idea of Turing machine had been introduced by Turing. Shannon had developed the theory of information. And the last two gentlemen here, McCulloch and Pitts, were the first who came up with a simple idea for creating very simple neuronal models that are described on these slides, which is really what is being used today in deep learning and neural networks. So in these models, a neuron is a simple processing device which has a number of inputs, let's say n inputs in the slides, and synaptic weights representing the strength of the connections of these inputs to the neuron. And the way the neuron operates is by taking the weighted sum of the inputs, the weighted average, the sum of the Wi, Xi, and then passing this weighted average through an activation function. And in deep learning, we use a variety of activation functions, but for instance, a sigmoidal function, such as a logistic or tanh function, is a typical activation function that is being used. We also use piecewise linear functions and so forth. This very simple model is really what we're using today in deep learning. And the key point is that the information is being stored in the value of these weights in a neural network, in a network of such neurons. And so the learning problem is really, how do you choose the weights of the network so that it implements the function that you're interested in? So when we're going to look at images, for instance, you have an X-ray and you want to detect whether or not tuberculosis is present in that X-ray, what you really have to do is to learn the value of these weights in the network so that it does the proper pattern recognition analysis, so that it can tell you whether tuberculosis is present or not in the input image. All right, I'm going to skip all this. The next important thing in the history of deep learning for images is the work of Hubel and Wiesel in the 1960s, where they started recording from cat visual cortex. And what they discovered is that in the primary area of the visual cortex, in areas like V1, you find arrays of neurons that really are acting like detectors for bars or for edges, where you have neurons that are responding to, let's say, a bar of a given orientation in the visual field at a specific location. And these neurons are repeated on a sort of lattice where they can detect bars at all possible orientations and all possible locations. So this is really the idea of convolving the image with these arrays of filters or feature detectors that are able to detect these patterns, very simple patterns like edges or corners everywhere in the visual field and at all possible orientations. There is a nice video of this on YouTube. I'm not going to try to play it. Maybe I can play it quickly, where you see the experiment of Hubel and Wiesel. You're going to hear the sound of the neurons. The recording is go through a microphone. And you can see in these experiments, they are moving bars in the visual field of the cat at different orientations. And when the bar is at the right orientation, you will see the neuron firing. And if you change the orientation or the location, the neuron is silent. Let me play this for a few seconds. Oh, the sound is off. I'm sorry, I cannot fix this directly, but I recommend you go on YouTube, just enter Hubel and Wiesel, and you will see this very interesting experiment from the 1960s. So the next step in the story, oops, how can I? The technical problem. I have lost the slides. I should have not played this. Let me stop sharing here. I'm not able to share screen again. Can you enable screen sharing?
You can.
Yes, now I can screen share. Okay. All right. So based on the work of Hubel and Wiesel, Fukushima in Japan in the 70s came up with the first idea of a convolutional neural network, which is basically a feed-forward neural network made of the very simple neurons that I described to you, the McCulloch and Pitts neurons, and was inspired by the work of Hubel and Wiesel. So in this architecture, you have convolutional layers, which are layers of neurons that are applying the same operation to the input, to the visual field at different locations. So the idea again is to have edge detectors, bar detectors at all possible location in the visual field and all possible orientation. So that was a very nice idea by Fukushima in the 80s. He called this architecture at the time, he called it the neocognitron. And the only problem is that is the problem of how you set the weights of the neurons in this architecture. And Fukushima thought of doing this using Hebbian learning, which was an idea that Hebb had developed in the 1950s. And that is a problem because we have shown mathematically that it's not possible to train such an architecture in computer vision if you're using Hebbian learning. And to really get this architecture to work, you need to use a different learning algorithm, which is nothing else than gradient descent. And when you apply it to neural networks with this kind of structure, the algorithm actually is called backpropagation. But the idea is very simple. You get input images, you have labels, you know whether, for instance, in an image, tuberculosis is present or not. So you start the network with random weights, and then you put in your images from your training examples, and you pass the information through the networks, you get an output, And you can compute an error, right? At the beginning, the weights are random, so you're going to get random answers. You compute an error, and then you simply change the weights by gradient descent in order to reduce the error. And you keep doing that through your training examples using this algorithm called backpropagation. And this is what we use today for training these architectures and many other architectures in deep learning for medical images and also many other applications. I'm not going to describe backpropagation in detail, but I will mention that already in the late 80s and the 90s, our group and other groups were using these methods. So we were using convolutional neural networks with backpropagation for solving computer vision problems. This was a problem of fingerprint recognition, where we used what is called today a Siamese convolutional neural network, where you have two branches that are essentially identical in the system, and you present a fingerprint image on the left, another fingerprint image on the right, and the system at the top has to tell you yes or no, these two fingerprints are the same, they come from the same finger, from the same person or not, right? So these are basically the techniques that we're using today, 40 years later. But of course, what we have today is much better computing power. In particular, GPUs have made a big difference for these problems because we can run very large network with millions of parameters. And of course, also the data. Because of the internet, because of databases and so forth, today there is much more data available for training such systems. Okay, so going to biomedical imaging today, of course, there is an explosion of data of biomedical images of all kinds and across different types of devices. So for instance, you can have X-rays, you can have MRI, you can have images taken with cell phones. There are applications where you can take an image with your cell phone of a mole on your skin and try to get some kind of diagnostic interpretation, and so on. Many, many modalities, and not only images, but I will show you examples from videos where you have, for instance, endoscopy and colonoscopies. You have the videos of the colon and you're trying to identify polyps. And I'll show you how we can do this in real time. And of course, the same techniques can be applied to X-rays and to problems in the field of tuberculosis. I'm going to skip a little bit of this theory here and go directly to the biomedical imaging application, which is what is of interest to you today. So let me skip these other applications in chemistry and other areas. And here are now the applications in the area of biomedical imaging. I'm going to give you a number of different examples taken primarily from work done in my group, but of course, this is a very active area of research, and there are thousands of scientists today working on deep learning and AI and their applications to biomedical imaging problems. So what you see in this slide comes from a new system that has been developed by one of my colleagues at UC Irvine, where he is able to grow blood vessels, these are blood vessels, what you see in green, in microchambers. So he can grow these blood vessels. And then you can, for instance, put stem cells or cancer cells in these chambers and let them grow. You can also give some drug to the system using the vascular system. And you can take images in a high throughput fashion. And what you really want to do is to decide, for instance, whether the cancer cells have been shrinking or not as a result of you giving the drug. So you see here how the pictures look like in this application. What you see in green are the blood vessels. The blue are cells, are cancer cells, right? And you want to take this picture at different times and decide, for instance, whether the drug was able to shrink the cancer or whether a drug is changing the vasculature, promoting vascular growth, for instance, and so on and so forth. And of course, you don't want to have humans looking at these images and making these decisions, right? Because it's very time consuming and laborious. What you want is to update the system. And so you can train these neural networks, for instance, to decide whether yes or no, the number of cancer cells has increased from one image to the next, or whether the vasculature has been disrupted, and so on and so forth. And so we just took a training set with our collaboration, Chris Hughes, and we had students label the images because we need to know what the ground truth is. So we need a labeled data set in general if we want to do supervised learning. And we trained a system, and we were able to show that it was very effective at this task. What you see here in this picture on the right is what is called the ROC curve. It's just one way of representing the performance of the system. There is a measure called the AUC. It's the area under the ROC curve, and a perfect system would have an area of 1. And you can see that the system here has an area of 0.99, shown by this blue curve, which shows very good performance for the network on this particular problem. This is another project that actually was started with Professor Flores for recognizing nanoparticles in images and their locations, whether they are located inside cells or outside cells. Again, another examples done on microscopy images. Here is a completely different example on X-ray images, so a little bit closer to the topic of interest to you. These are mammograms. So these are X-ray images of the breast, and there are millions of mammograms, 40 million mammograms in the US alone per year. So if you think worldwide, we have hundreds of millions of mammograms done each year to screen for breast cancer. And so you can train a system to detect yes or no whether there is evidence for breast cancer in a given mammogram. And there are people working on that. But in this particular application, we worked on something else, which is predicting the degree of calcification in the given image, right? So it's not a classification problem, it's a regression problem where you want to predict essentially the total calcium mass present in a given image. You can see here the true calcium mass versus the predicted calcium mass. And you can see that there is very good agreement in this red line between the true value determined by the radiologist looking at these images and measuring the calcium present in the image, and the predicted value done with these convolutional neural networks, this deep learning approach, right? Now, the reason for doing that is very simple. It's that a high level of calcification is a potential sign for heart disease. So as a byproduct of being screened for breast cancer, you could also be screened potentially for heart disease, so that if the system detects a high level of calcification, then the recommendation is for you to undergo additional tests to see whether perhaps you also have a problem, a heart disease, right? Heart disease problem. So this is another interesting example of application of deep learning to biomedical images. Here is another applications that we worked on. It's the detection of cancer metastasis to the spine. So the spine is the third most important place where cancer can metastasize. The other even more common places are the liver and the lungs. but in this case, we were looking at the spine. And so again, in these images, we want to detect whether yes or no, there are metastases that are present. And if they are present, we want also to know where they are. So identify their location. And again, we developed deep learning methods together with our radiologist collaborators at UCI for detecting these cancer metastases in the spine and identifying their location. To identify locations, by the way, and to draw bounding boxes around regions of interest, this can be done with the same methods because you can have, again, a feed-forward convolutional neural network. And then it can be trained. You can have one output that says yes or no, there is cancer, or there is a particular diagnostic in the image. But you can also in the output include things like XY coordinates for the bounding boxes, right? So if the disease is present, right, if you have a 1 in the output that does classification, yes or no, there is a disease, you then also have other output with XY coordinates that tell you where in the image you should look or you should draw a bounding box for the relevant diagnostic features. So you can use networks not only for classification, but also for localization of regions of interest. And I'll show you an important application of that in a few minutes. Here's another example. This is working with dermatologists, looking at images of the scalp. And what you want to do there is to identify hair follicles. And again, draw bounding boxes around hair follicles and count them. The reason you want to do that is that if you're developing a hair treatments product or drug that is supposed to promote hair growth for people who are losing their hair, and you want to do this in a very scientific way, what you have to do is to take a patch of your scalp and take images at different points in time throughout the treatment and be able to very rigorously count how many hair follicles are present in that patch at different points in times. And again, you need this kind of technology for doing that. And it would be very tedious to have humans trying to look at these images and count the number of hairs, notwithstanding that you have to do it for many images over an entire patch, not just one vertical slice. This is another example of application of convolutional neural networks. This is for classifying gliomas. These are brain tumors. I want to go into the details. You can look at the references. Just again, I want to mention that there are many other groups working on this. This is work, for instance, from a group at Stanford that developed the application where you can take a cell phone, take a picture of some mole, some irregularity that is present on your skin, send it to the cloud, and have a neural network in the cloud, apply these deep learning methods, and send you back a recommendation on whether, for instance, your mole should be checked because it is potentially malignant, potentially a sign of melanoma or not, right? So this application can be very useful for deploying in developing countries, for instance, where medical care is not readily available everywhere. You could imagine a situation where you have very cheap technology, imaging technology, where people could take images of different kinds and send them to the cloud and get some important information back on whether to seek further testing or not, right? Now I'm going to show you a different type of applications. These are applications to videos, to endoscopy. And so this is an example of an application for colonoscopy. again, a very common procedure that is done millions of times every day in the US alone, where basically an endoscope is inserted in the colon. And what the doctors are looking for is for polyps. So polyps are these structures that you see in these green bounding boxes. And colonoscopy is typically lasts, a few minutes, 5 minutes, typically. And the surface of the colon, to give you an idea, is about the surface, the size of a tennis court. So it's not uncommon for colonoscopy to miss colons, to miss polyps, because this procedure is done fairly rapidly. And so it would be nice to have an automated method that can detect polyps and alert them to the presence of polyps. So what you would like is to have a system, an AI, that looks at the video and identifies polyps or potential polyp regions and puts a bounding box around such regions. So in collaboration, in this case with Bill Kearns, with a colonoscopist here at UCI, he gave us about 7,000 images of the colon, some containing polyps and some, of course, without polyps. And so we trained a convolutional neural network to classify those images into two classes, with polyp or without polyp. And we also trained the system to place bounding boxes around polyps when they are present, using the approach that I described to you. Now, this is nice, but this applies only to images. And the question is, how can you extend this approach to videos? And the answer is that it's very easy. You don't have to do anything, because when you're training the neural network on images, the training can take a lot of time. It depends on what kind of hardware you have, whether you have GPUs or not. But it is not uncommon for training on these problems to take 1 week or 2 weeks to complete. However, once the neural network is trained, it can produce predictions very fast, in something like 20 milliseconds. So when you have videos, even if you have, let's say, 60 frames per second, I don't have to apply the neural network to every frame. I just apply to, every 10 frames, for instance, is plenty. So you get plenty of such frame per second, and you have the time in 20 milliseconds to do prediction on those frames. And you can even use neighboring frames and combine the results to get more robust inferences, right? So if you have, let's say, 10 frames that says there is no polyp, 1 frame there is a polyp, then 20 frames that say no polyp, probably that the frame that says there is a polyp is a false positive, because it's surrounded by many, many frames taken very fast within a second, and all the other frames do not contain a polyp, right? So you can clean up the signal further just by combining different frames, neighboring frames that are coming at a very fast rate. So let me try to show you the movie. So I have a movie where you have a collage of different colonoscopy clips. I hope this is not going to create a problem again. There you go. So this is a collage of different colonoscopy. And what you're going to see is the colon, and you're going to see our AI system putting a bounding box around polyps in real time with very high accuracy, comparable, if not better, to the accuracy of human doctors. This system is actually now deployed in the clinic. It's being used in the clinic to help in actual colonoscopies to avoid missing any polyps. It's not yet replacing humans, of course, but it's helping human. It's the AI working with human experts to help them be more thorough and avoid missing any polyps during colonoscopies. Okay, you get the picture. Now I'm going to show you yet another example of application to video. This time it's going to be to completely different videos, which are done under microscope for when people are doing surgeries on the eye because of things like glaucoma or other eye diseases. And when you're doing these surgeries, there is something very important, a marker that is very important, which is called the trabecular meshwork, the TM. And you can see it here on the left. This is the TM. It's this very thin line, and it's very difficult to see it, even for experts. In some cases, it is almost transparent. So it would be nice to have a system that can assist eye surgeons during surgery and sort of delineate or show them where the TM is in a given image. So again, we did the same thing. We got images of the eye during eye surgeries from our collaborator, Ken Lin, at UCI. And of course, the expert had manually labeled the location of the TM, of the trabecular meshwork. And so we were able to train a system consisting of a neural network, again, a convolutional neural network, to identify the location of the TM. This is not just a bounding box now, but we really want to sort of delineate the contour of the TM in real time, if you want. And again, the system is trained on still images, but it can be applied to video using the same approach, essentially, that I described for colonoscopies. And I'm going to try to show you the system. Again, I have a video here. You can see in real time, during eye surgery, you can see the lines that are produced by the system identifying the location of the TM. This is not yet used in the clinic. We are still developing this, but we hope in time to be able to deploy this in actual surgeries. It's almost finished. In any case, this should give you an idea of how these techniques can be applied and are being applied to tuberculosis, to the identification of the disease, potentially the localization within images of the lungs of areas of interest. And actually, I'm going to show you an example of such an application, I mean, applications to X-rays of the lungs, but for a different disease. And actually, I'm going to show you an example of this application in veterinary medicine. So there is a disease called valley fever, which is produced by a fungus that can be inhaled. It's the most common systemic mycosis in dogs in the southwestern United States. And it's actually a disease that is going to expand and become increasingly more problematic because of global warming, right? Which promotes the expansion of this particular fungus. And it actually can be transmitted to humans. So it can also become a problem in humans. But in this case, we decided to work with veterinarians. And so we acquired images of the lungs, X-rays of the lungs from many dogs with and without the disease. And again, by now you should know the story. We trained different neural networks on these images. You can see here the ROC curves, which are very good. These are different neural networks that we train. So the green neural network looks like it's the best, has a very high AUC of 0.991 for detecting this disease. And this is how it looks on the X-rays. You can see the original image. And then again, using these neural networks, we can predict in this case that the disease is present, and we can provide regions of interest that radiologists can look at further. And so you could imagine doing exactly the similar things for other types of lung diseases, including tuberculosis. Now, the case of dogs is particularly interesting because there is a high variability among dogs across dog species in size and anatomical features, etc. The variability is even greater than in humans. So we were very happy to see that we could apply these methods also to the case of dogs, where you have this very high degree of variability. I'm going to skip these other applications to clinical data and try to conclude the talk with some remarks and then follow with questions and discussion. So generally speaking, deep learning, feed-forward neural network, recursive neural networks are very effective and flexible. They can be applied to all kinds of data and problems. We dealt primarily with images and videos in this presentation, but of course you can apply similar techniques to text, to graphs, to molecules in chemistry, to data from sensors, etc. This is why, you know, AI is expanding very rapidly these days, and you see application of deep learning to all kinds of areas, way beyond biomedical imaging. Within imaging, CNN, convolutional neural networks, are the most effective approach so far that can be applied across all kinds of imaging modalities and sensors, whether it is you know, electron microscope, regular microscopes, X-ray, MRI, you can use ultrasound, video, endoscopy, cell phones, etc. It doesn't really matter which kind of modality you're using. We're working with astronomers, you know, using all kinds of images from telescopes, for instance. So you can apply to all these different imaging modalities, and of course across all kinds of diseases and pathologies, including tuberculosis. The key problem is not the neural networks, actually. The key problem is the data, is getting enough data to train these systems. Now, it used to be the case that if you are training a very large neural network with a lot of parameters, normally you would need a lot of data to train such a network. And this is a problem, of course, because you need labeled data, and labeled data is expensive to acquire. And in addition, in the medical field, sometimes there are you know, privacy or legal issues that prevent you know, obtaining or aggregating a lot of data. However, there are a number of techniques that can help you when you don't have a lot of data. Even if you have, let's say, a few hundred images, or even in some cases, a few dozen images, we have been able to apply this technology, even using networks that have millions of parameters. And the kind of things you can do are things like data augmentation. So if you give me, say, an image of the lungs, I can create additional images artificially by adding noise, by rotating the image a little bit, and so on and so forth. So by applying certain transformations. There are other techniques such as regularization and dropout that can be applied also, that will help you avoid overfitting to a small training data set. And then I think the most important technique that has been widely used in recent years is the idea of reusing pre-trained models. So you have models that have been trained for general purpose vision, you know, to recognize pedestrian, cars, trucks, trees, etc., you know, natural objects in the world, very large networks that have been trained on those tasks that are very good at what they are doing, and they are publicly available, so you can download them. There is something called VGG16. You can download that neural network. It's a big neural network that can recognize interesting objects. Now, of course, it's not trained for the specific purpose of tuberculosis, but all the layers of the network, all the lower layers, are still useful because they are trained for general purpose vision to detect edges, corners, and so forth. So you can use all the lower layers of the network trained on general purpose vision tasks, are good as they are, you can use them. And the only thing you have to do is to retrain a thin layer at the top for the specific purpose of detecting tuberculosis, for instance, right? So the top, you just have a few parameters, just the top layer for the final decision, and all the rest, all the lower layers can be sort of stolen, taken from these networks that are publicly available that were trained for different tasks. Another things that is worth knowing is that there are techniques for compressing these networks, for making them smaller. This becomes important if you need to deploy your neural network on devices that don't have a lot of memory storage, maybe on cell phones or other devices. So there are techniques for compressing these networks. And in a sense, you get a feeling that for biomedical imaging, almost all problems have been solved. We have the technology for doing these tasks. All you have to do is really get the images, then do the training. There are a few technical problems that are still challenging in biomedical computer visions, things like 3D convolution, dealing with very complex image semantics and so forth. So there is still interesting research to be done, but all the basic tasks, say, of classifying images for diagnostic purposes, I think for all those basic tasks, we have technology available today that is very successful. It can achieve performance that is on par, if not better, than human experts. And then there is the black box problem, the fact that people are worried that when you train these networks, you don't really know how they work inside, right? They have a bunch of parameters, of weights. They've been trained from the training set, but you don't know exactly what the network is doing. And to address this problem, there are also a number of techniques, but it is to be expected that neural networks are somewhat opaque, because what they are really doing is taking your training set and shattering it across the weights of the neural network. And this is not a reversible process. Even in very simple cases like linear regression, if I give you the coefficient of the line, you cannot go back and retrieve the training set, right? The training set is being compressed by the learning algorithm into the weights of the system, of the parameters of the system. And so it is not surprising that things are very opaque. Nevertheless, you can try to open the black box, so to speak. There are ways of developing architectures that are more interpretable, more explainable. And I think a very important lesson is also that you should use as much as possible encapsulation. This is a general idea from software engineering, the idea of encapsulating, of dividing the problem into sub-problems that are easier to address. And this is very useful also when you deploy neural networks. So for instance, to give you an example, when we are training neural network on polyps, we have different tasks. We have the classification task, is there a polyp or not? But then we have also the localization task that to determine where the polyp is in the image. And that is very useful for understanding what this neural network is doing and for addressing problems. For instance, if you have false positive, the neural network tells you, I think there is a polyp in this image and it's a mistake. Then you ask the network to give you the bounding box. And so you see the region in the image that caused the network to produce a false positive, okay? And by looking at that region, you can understand what is it in the images that is leading to these false positives, and then you can try to correct that. In our particular example, we saw that surgical instruments were sometimes present in the image and were causing the network to call a false positive, even in the absence of polyps, but in the presence of surgical instrument. And so you can fix that by training a system on surgical instruments alone and then subtracting that and so on and so forth. The real challenges are getting the data, and then once you have trained the system, it's to deploy the systems in healthcare settings, because there are all kinds of issues of privacy, of security, legal issues of radiologists and doctors being worried about losing their job because AI is taking over their jobs, and so on and so on and so forth. So there are many interesting also technical and societal issues that are useful and need to be addressed. Okay, I'm out of time, so I'm going to stop here. Thank you very much. If you're interested in more details on these techniques, I can recommend that you look at my book, and I'll be happy to try to answer any questions. Thank you very much.
Muchas gracias, Professor Baldi. Muchas gracias.
Thank you, Professor Baldi. Thank you for such an important and interesting information that you've just given us. Let's move on to the questions. I have a few, so let's begin. The first one says, do you have knowledge of any system to detect lesions suggesting tuberculosis in humans? And if any exists, what type of images do you use?
I will answer in English. I personally have not worked on tuberculosis directly. I've heard of other groups working on tuberculosis, and you could try to do a literature search. Let me also mention that we would be delighted to collaborate with any group in Mexico if they are interested. Again, the key issue would be to get the data and provide us being able to share the data with us. Then we could train a system and give the system back to you for further testing and deploying in your setting. So really the key task is for the clinicians to aggregate data, at least a few hundred, ideally a few thousand images is probably enough. It could be X-rays, it could be other types of images. With and without tuberculosis, we need images of the healthy lungs and lungs with the disease. If you want to detect specific markers, we need bounding boxes around those markers. So that's, there is work, labeling work required from the radiologists or from the clinicians. But if you're able to produce those images, then it's relatively straightforward to deploy these techniques. You do need, good computing powers, good GPUs. We can provide that to you, or you can try to buy such machines in your setting, and then you can train these systems and deploy them.
Muy bien, muchas gracias. Tenemos otra pregunta que va un
Thank you. We have another question, which is a little bit related to the last one. Do you have knowledge of any work that applies deep learning to support the diagnosis or monitoring of tuberculosis? What is the most commonly used method?
I apologize, but tuberculosis is not an area I have worked in. So I cannot tell you, what systems are being used and who is developing those systems. Of course, you can do a search in Google. You would find some articles. That is the best thing you can do, I think.
Gracias.
I think the next speaker actually.
Otra. Nos preguntan.
Sorry, I wanted to mention, I think the next speaker has actually worked on tuberculosis. So you will see examples of applications of deep learning or other methods to images from tuberculosis patients.
Sí, muy bien, gracias.
Thank you. Another question we have here is how long does it take? How long between the time we pose the problem, the deep learning problem, and
there are
applying
many
it?
stages. So the first stage is the collection of the data. That is on the clinician side. This is not something we do. The clinicians have to again produce at least hundreds, ideally a few thousand images, both in the control case and the disease case. Once we get the images, you know, we are experts in CNN, in deep learning. We have done this so many times. So we can start training systems right away. So in a few weeks, we can have a prototype. Maybe 2-3 weeks, usually we have a prototype. We may need a little bit more time if the problem is very complex or if we need to do something special. But again, a few weeks of training using GPUs, we can have a prototype. We can give it to the clinicians for deployment in the clinics. Now, then it has to be tested in the clinical setting. That can take, you know, a few months. If you want to go to the next level, you can do a clinical trial that takes even longer, may take a year or two. So it's a you know, from conception to a product, the whole pipeline could take a few years. But our part, the computer science part, which is training a system, can be done very quickly in a few weeks. And then we can pass the system to the clinician for, you know, testing in a clinical setting. And of course, as you test things, you can get more images that then can be sent back to us, and we can train the system even further so that the accuracy goes from 98% to 99 to 99.9, right? So as you get more data, you can keep training and refining the system so that it gets better and better. And of course, you can expand at the diagnostic level, right? From the same images, you can do breast cancer, then you can do calcification, then you can do some other diseases, right? Same thing in colonoscopy. We can do polyps, no polyps. Then we can do pre-malignant polyps, healthy polyps, cancer polyps, and so on. So you can get a more fine-grained classification of your images within your disease or across 2 or 3 different diseases and deploy those. So there is many opportunities for refining and expanding the system after the first stage where you develop the first prototype. I hope this answers the question.
Sí, muchas gracias. Es muy interesante todo el proceso.
Yes, thank you very much. The process is very interesting. Above all, the fact that the application goes directly into healthcare to benefit many people, and the accuracy is really interesting. Congratulations for all your work. I think you are one of the most important researchers in this area. And I think we just have time for one more quick question. The problem with the data, for example, how can we avoid overtraining neural networks if we have little data?
That is a
training?
very good question
that
I mentioned. So if you don't have a lot of data, you have to be very careful to avoid overfitting. And there are a number of techniques for doing that. One technique I mentioned is to produce more data artificially. That's called data augmentation. So if you give me only, let's say, 10 images, I am going to artificially make 100 images out of your 10 images by adding noise, you know, Gaussian noise to the images, or by doing a geometric transformation. Maybe I rotate the images a little bit, you know, 1 degree, 2 degrees here and there, or sometimes you can do symmetries and so forth. You flip up and down, right and left, whatever, it depends on the problem, but this is called data augmentation. So I make more new, I create new images from the data set that you give me. The other very important technique that I mentioned is using a neural network that has already been trained on a completely different problem, on a completely different computer vision problem. So you take a big neural network, even 1 billion parameters, that has been trained by Google or by Facebook on millions, if not billions of images. It is trained to recognize faces or to recognize whatever, you know, self-driving cars. They have neural networks recognizing the streets, the pedestrians, the car, the bicycle, whatever, right? This network is still very good for you. It was not trained for tuberculosis, but it was trained for general purpose vision. So a lot of the layers in the neural network are good for tuberculosis because they are general purpose. They detect edges, they detect corners, and so forth. So you just train, these networks are available for free on the internet. You can download them. You have the weights of the neural network, you download them. And this network is pre-trained. So what you have to do now is to keep all the layers, all the lower layers that are general purpose vision layers, and you remove the top layer because you're not interested in self-driving car. You're not interested in driving car. You're interested in tuberculosis. So at the top of the network, you put a little layer with maybe 1,000 parameters that is specific for tuberculosis. And then you use that network. You just train the top layer for the tuberculosis using a small data set, relatively small data set. If you have 1,000 parameters, it would be nice if you had, 1,000 images or at least a few hundred. But you don't need millions of images to do tuberculosis using these networks that were trained for a completely different purpose. And if you think about it, this is what happens with the humans, the radiologists, right? When the radiologist looks at an X-ray images, his visual system was not trained on X-ray images. It was trained as a child to recognize toys, to recognize mom and dad, to recognize brothers and sisters, and so on, right? So the human visual system is not trained on X-rays images. It's trained for general purpose vision. But then when you go to medical school, you spend a few months or a few years to train yourself on those specific images, right? And so that's basically what we're doing in the, in AI, in the artificial neural network world. We're using a general purpose neural network. Most of it is already very good. And we just train the top for the specific medical task that you're interested in. So that's very powerful and very fast to deploy, because most of the work was already done by Google and Facebook and all those guys. And they have a lot of images, a lot of computing power and so forth. And it's available to everybody anywhere in the world. So if you want to know, you can email me and I'll be happy to give you pointers, tell you, which architectures you can download. There is, many of them. One of them is VGG16, but there's many others. Mobile nets, smaller ones, and so on and so forth. ResNet, many such architectures. Gracias. ¿Otras preguntas?
Muy bien, muchas gracias. Muchas gracias por todo.
Thank you so much for all your knowledge. And actually, it's been very valuable information for all of us. And you have been very kind for sharing all this with us. We have more questions. Unfortunately, we don't have more time. We want to thank you for your time. And now we have to pass the floor to our next speaker. Thank you, Dr.
Thank you very
Baldi.
much. Send me email if you have more questions.
Sí, seguro. Muchas gracias. Haremos llegar las preguntas.
Muchas gracias. Adiós.
Hasta pronto. Bien, ahora vamos a darle la
Okay, now we're going to pass the floor to Professor Shizhen Queen, who works for the United Nations Office for Project Services. She's currently working in Stop TB partnership in UOPS as a specialist in digital health. She has been managing innovation projects since 2015 with a digital health approach, including AI, digital adherence technology, and connectivity solutions, leading the digital health office in desktop TV. She is also working closely with all the shareholders and stakeholders locally and internationally to facilitate the introduction, the global introduction and the deployment and the evaluation of digital solutions, proven digital solutions, and also addressing interoperability issues, security of data. She also leads the greatest international evaluation for products regarding AI for TB detection, which also helps or contributes with the first recommendation by the WHO regarding the use of AI for these purposes. Okay, now Dr. Singh, she's going to present a document regarding innovation in X-ray and artificial intelligence computer-aided detection CAD software for TB response and availability for this technology. Thank you so much, Doctor. The floor is yours. Let's give her a moment. I think there is a technical glitch right now. Let's just be patient so we can reconnect with her. There you go.
Muy bien, en un segundo entrará.
She'll be here with us shortly. Can you hear us? Can you hear me?
So if the video has some problem to show, I can try with my internet, but I don't have access to share my screen.
Ok, vamos a darle los privilegios para compartir su pantalla.
Okay, we'll fix that for you right now.
¿Puede intentarlo nuevamente?
Can you try that again, please?
Ya está.
There you go.
Adelante.
Okay.
Okay, 1 second. So just put this on. Let me just switch. Hang on, let me just switch my camera on, but I don't see the button. Okay. Can you see my screen? Can you see me?
¿Se ve la pantalla? Sí, ya.
We can see
ya.
the screen. And now we can see you. Now we can see you. Welcome. Thank you so much.
Great. Hello, everyone. Good morning, good afternoon, good evening, depending on where you are. So my name is Zhizhen Tian. I'm a digital health specialist from the Stop TB Partnership. It's my pleasure to present today on the innovation on X-ray and AI software for TB response. So, okay, see if this works. Please let me know if if you cannot see my screen, if there's any technical glitch. So I think we all, without surprise.
Sí se ve la pantalla.
Yes, we can see it. We can see everything. It's fine.
Okay, great. So yeah, I think we're not surprised to find that the current COVID-19 pandemic has a devastating impact on the global TB response. Maybe perhaps we'll still be shocked by the number. By later this year, we've seen in the WHO Global TB Report, which published the TB notification for last year, 2020, When that shows only 5.8 million people were diagnosed and notified that year. This compared with 2019, the year before, where 7.1 million people were diagnosed and notified. This difference is 20% decrease in case notification. Then maybe that's not a surprise to know that in 2020, we're seeing for the first time an increase in TB mortality since 2005. This effect is likely to be long-term, according to a modeling study done by the Stop TB Partnership. A continued 4% to 16% increase in TB mortality will occur in the next 5 years. So all of this underscore the importance of increased funding and effort to address the increased diagnosis gap and to reach those that are most vulnerable. WHO has guidelines that recently published policy updates on systematic screening. By saying systematic screening, what we mean, this is a definition from WHO, it means that it's a systematic identification of people at risk of TB in a predetermined population by some kind of assessment using examination or test or other procedure. Systematic screening tests can be used to distinguish those that are likely to have TB from those who are unlikely to have TB. So it's important to know screening would only be used to triage and screen TB. The confirmation diagnosis is still needed by evaluation using one or more diagnostic tests or clinical assessment. So the TB screening has an important role in the overall TB care. We know that TB screening is important to find out those who would normally be missed by healthcare system, which is underscored by the importance of the devastating impact of COVID. TB screening is important to reach the most vulnerable group who are often left out or don't have access to care. Finally, TB screening is important to identify those who needed to be put on TB preventative treatment, to prevent the progression from latent TB to active TB. In March 2021, so March this year, WHO has reviewed new evidence and new technological advances around the TB screening and updated the policy around population screen. This policy updates and accompanied with the operational handbook, those can be found on the WHO websites or through the link here. This new policy updates recommend the following key population to be screened. And this recommendation is strong recommendation without additional consideration. There are other key population listed on this slide that were recommended by WHO as a conditional recommendation. Systematic screening for TB should be considered after weighing the benefit and risk, and also considering the opportunity cost for other TB and health intervention. Prioritization of risk group that represent a higher burden should be high burden of TB should be considered. Now, in terms of tools to be used to screen TB in general population and in high risk groups, WHO recommend those 4 type of tools: symptom screening, checks X-ray, computer detection, which is powered by AI, and then molecular, WHO recommended rapid tests such as GeneXpert or TrueNet. For today's presentation, we'll be focusing on talking about the 2 in the middle. So I think X-ray, we all been using them in general health systems, so we know it's not a new technology. And checks X-ray as a technology has been quite useful for TB screening identifying active TB. Because X-ray is more sensitive than TB symptom screening, a lot of asymptomatic individual will not be found if X-ray are not being used. X-ray can also help to improve the efficiency of gene expert use. However, in the past few decades, the use and access to X-ray has been hampered by the lack of X-ray facility in peripheral setting, and there's a lack of trained radiologists. Even when radiologists are available, the inter and intra-reader variability can be quite high. However, we have hope. We have things to hope for because with the advances in both the hardware and software, we're presented with new opportunities. Let's first look at the X-ray technology. So there are three types in terms of X-ray technology. And I'll go from the left to the right by more historical and then more advances. So we all have seen those analog film that needs to be developed in the wet room. So this is the most traditional methods of X-ray imaging. The X-ray receptor will require a film, analog film to be used, and the wet process will be required to develop the film in a dark room. There are some obvious limitations with these X-ray equipment because there's special trained personnel needed to develop the film. Furthermore, the output of these X-ray machines are physical film, and there's no digital format that can be unless you use a digitizer. Then integration with PAC system, because the output is not being digital, is impossible. And reading by AI or CAD software is also not possible unless a digitization process occurred. Because the manual nature of the process, the throughput is much lower and the radiation dose efficiency is poor. In between, we have ultrafaded and computed radiography, the CR. They combine analog X-ray generator with a newer digital detector or reusable digitizer or CR reader. This type of X-ray system is, as you can see, going between analog and digitals. The X-ray output indeed will be in digital format. And the image processing will no longer require manual input and will no longer require wet process. Instead, it will be automated. And the integration with PAC system and interpretation by AI software is possible. The radiation doses efficiency indeed is higher than the analog X-ray system, but it's lower than the system that I will be talking about. So for digital X-ray, this is probably what's mostly be used in developed country, but we're still seeing they're being used in a lot of high TB burden country. They're less used in high TB burden country. But these represent the latest development in X-ray technology. And some new exciting development is also that I'll be talking about that is also in the digital X-ray categories. So both the X-ray generator and the X-ray detector are completely digitized. The output is completely digitized, and integration with PACS and integration with CAD AI software is completely digitized. And the image quality are much better. Radiation dose efficiency are much better than any the other process that I talked about before. So as I mentioned, in terms of, within the digital X-ray type of technology, we're also seeing new technology advances, particularly with the type of X-ray system. Here we're grouping them by portability. Stationary X-ray are those heavy-duty X-ray that install in the hospital that are used for general radiography. So in addition to TB, and they can accommodate heavy workload, and then they're usually connected to main electricity grade. The image quality from those stationary X-ray are excellent, are being used as a benchmark. Now, mobile X-ray system, they're the one that can be moved or rolled around, will be mounted on a truck, then be transported to another location or in a community. And those trucks can be lead protected, then the implementation of the X-ray system can be used in the field without lead wall. And these type of X-rays can accommodate moderate to high workload. And some products allow for battery power for intermittent use. And the image quality of these X-rays are typically very good. Finally, the last X-ray system is what's most exciting for us nowadays, is this ultra portable type. They're so ultra portable that you can hold the X-ray generator. There is one product that even looks like a camera. You can hold it by one person in your hand. And these X-ray can be carried by a few people without the trucks or van to a community setting. Because they're more portable, they're more lightweight, so they're also less in terms of workload. But the benefit is they're battery powered, and the image quality is quite acceptable. The image radiation generated from those X-ray machines are much lower than the other X-ray system that I mentioned before. Here showing the latest technical specification developed and published by WHO and the International Atomic Energy Agency. This guidebook came out just a few months ago. And it will help to support decision-making regarding the selection, the integration, and allocation of this type of X-ray system in countries that are interested in importing and using this technology. So today we'll be focusing on the ultra-portable type of X-rays. As I mentioned, there's some clear advantage of ultra-portable X-ray. Decentralization of X-ray radiography is made possible with this type of X-ray technology because they're built on battery, so it's possible to use X-ray assessment in completely off-grid setting. The low weight reduce a lot of physical strain on the staff carrying and setting up the system. There also much reduced radiation in the output, in the X-ray generator output, which made it possible to use in the field without lead wall protection in certain country, and also possible for some vulnerable population who would normally not be recommended for using X-ray. And the image quality is comparable to stationary X-ray. However, it's important to know that there are also some disadvantages come with the ultra-portable X-ray system. So the portability does come with compromises. Notably, stability, the population suitable for these X-ray, and the internet requirement, electricity need, and throughput. The reduced battery life when you operate this device completely off-grid can limit the throughput of the X-ray assessment program. Indeed, the overall system can be quite portable, but for the consideration of the safety and stability of the system, maybe more heavy duty detector and generator stand might be more preferable by a radiographer to the currently more stable, more portable supporting stand. And those more portable supporting stand doesn't have any automation when you adjust the height of the generator and detector, which require more manual work of the radiographer. Still, those X-ray machines are being portable, but still need more than one person to transport. Finally, one disadvantage is that there currently lack of international guidance on radiation protection regulation suitable for this type of X-ray system. And we have seen in some country very strict protection regulation were in place, which has limited the application of this portable X-ray in the field. Now I want to talk about the option for procurement, keeping in mind there are several more products, more ultra-portable X-ray product currently exist on the market. But at FoVI-TB, we have a global procurement, which we call a global drug facility, GDF, that provides a global cataloging for TB treatment and diagnosis. In the catalog, we have currently two ultra-portable systems. The first system listed here is provided by Delft Light. The entire system is composed of the X-ray generator, the X-ray detector, the X-ray console laptop, and a slightly more heavy-duty X-ray generator stand, and a mounting system for the X-ray detectors. There are several replacement battery and charger are equipped in the package, as shown here. And also a solar panel with inbuilt battery bank also included in the package. This battery, this solar panel can be, because it comes with the inbuilt battery bank, so it can be charged with sunlight or with electricity grid. We also provide in the full kit one lead apron that's not showing in the slides. All of the equipment except for this generator stand can be packaged in this backpack for transportation. The overall system, including all the components, weighs in total 33.2 kilograms. The alternative solution we have in the GDF catalog is Fujifilm FDR-XR. Perhaps some of you have seen this from other places because the iconic X-ray generator looks like a camera, normal camera. And then this camera is only 3.5 kilograms. Then we also do provide this X-ray generator, but the full kit also has the X-ray detector, the X-ray console laptop, the supporting stand for the generator, and the detector for Fujifilm FDR-XR is more lightweight than the previous product. There are tripods. Again, when you need to adjust the height, you need to be manual. Also, replacement battery are provided, and a power bank is provided instead of a solar panel. Similarly, lead apron and some radiation protection accessories are provided, like shock indication stickers. Finally, a carrying case. This is 10 kilograms, this carrying suitcase, which is specially built to fit the whole full kit so that everything can be packed inside except the lead apron, but everything else can be packed inside and transported securely. The whole kit in total weight close to 30 kilograms as well. I'll just quickly show you the price of the two systems when procured through GDF catalog. Just keep in mind, this is the equipment cost. The additional costs are service, such as installation and training and warranty extension. The equipment costs come with 1 year warranty built in. Now, I want to go to the software side. I think my previous speaker has explained very well what AI technology is, so I'll just skip this slide. Indeed, there are a lot of deep learning neural network application in TB in terms of reading X-ray, chicks X-ray. I would just going to show you quickly what those AI products in general output looks like for TB products. So in general, how it works is an AI or CAD product receive digital X-ray or digitized analog X-ray film. Then they use neural network. Majority of TB AI products also use a neural network to analyze digital X-ray for sign of TB. And this process can be done with or without internet connection. So in general, when each X-ray is received, CAD can produce the abnormality score between 0 and 1 or 0 to 100. With a higher abnormality score associated with higher likelihood of TB. A heat map that shows the areas of abnormality detected by the AI software. The color indicate the higher abnormality prediction by the AI. Then some AI product can provide a binary classification, which is based off on the abnormality score. The binary classification, the naming itself differ by the product. So basically it says, oh, it's TB present, a TB abnormality present or not present. Some of the commercial products can summarize AI finding in a customized report format and similarly to radiologist report. We're also seeing CAD products are increasingly offer a number of add-on features such as data dashboard for patient register, for presumptive TB registering. Now, as I mentioned, there are plenty there. A recent landscape study done by us and FIND that were published in March this year identified at least 28 CAD developers. When I say at least, it's because those CAD developers we identified, some of them has refused to participate in the study. So there are at least, so there are definitely more than 28 such AI company exist working on TB, working on X-ray, sorry. Out of those 28 company, 12 of them have a TB specific product or a TB specific module, and they're currently on the market. And 7 company and 7 products on the market currently have CE marks. We're currently undergoing annual updates, and I'm already seeing numerous new names popping up in the industry. So you can have a look at the current landscape report to see what are the products available on the market for TB by logging into this AI4health.org website. In summary, among the numerous CAD commercial products on the market, the common characteristics includes most products is only suitable for people above 15 years or older. most products read posterior anterior DICOM digital X-ray images. Slightly more products can read anterior posterior images, and very few products can read lateral images. And JPEG and PNG are also widely accepted format for for AI products. As I mentioned before, the radiologist style reporting is becoming more popular. Online and offline is becoming, internet dependency is not an issue for commercial products. And integration with PAC system or other clinical information system is often offered as a service by commercial company. And the integration with most of the main X-ray, mainstream X-ray system has been offered by most company. These CAD products, they are vary in some ways. Some products can tailor their product performance using customers' data or local data. Some of them even offer a continuous learning feature. As the name suggests, the algorithm will improve or it will change as new data are being fetched, are being read from the client every day. And some of the software may require additional training before you can even use them. Some software offers, in addition to TB, report on other non-TB abnormalities. We also seen this becoming frequently asked by country and program. However, there is a lack of independent evaluation data on the performance of CAD for differential diagnosis and how accurate it localized the abnormalities. Now, when I talk about accuracy, so what's the performance, what's the diagnostic accuracy of CAD when it comes to TB detection? So in 2020, for this year, the policy updates, we had several guideline development group meeting in 2020. They independently evaluated 3 independent evaluation. We have contributed to one of the 3 evaluation. And those evaluation look at 3 different CAD software for detecting bacteriologically confirmed TB. The reference standard used in the GDG group evaluation was either culture or gene expert. And we look at a range of population and setting. The results come out from the independent evaluation shows, yes, there is a variability, of both human reader and CAD software in different setting and different population when it comes to detecting TB abnormality. But there is a substantial overlap in the sensitivity and specificity of human reader and AI software. This suggests that there's little difference between the two. Based off this result, WHO has recommended for the first time that CAD AI software can be used to replace human in screening and triage setting, which I will show that later. This evaluation also implied that also shows that in many settings, healthcare provider often don't have sufficient training, but they were being tasked to interpret X-ray. And maybe in these cases, CAD may even perform better or even more favorably in comparison. So in this paper that we published on Lancet Digital Health in September this year, and we looked at in the largest head-to-head comparison of 5 commercial AI software for TB. They're listed here. And we're also using the latest version. The study shows a significant outperformance by the CAD software compared to local radiologists. And the study was done in Bangladesh and in Dhaka metropolitan cities. So the local radiologists were the brightest and the best in country in Bangladesh. The study also showed that all 5 commercial CAD AI products were able to reduce the subsequent expert tests by half while maintaining a high sensitivity above 90%. There are significant differences in subgroup analysis, particularly in older group and those with prior TB history. This is where commercial CAD product doesn't perform as well as in the other subgroups. So you can see the AUC, as mentioned by the previous speaker, was used to evaluate the overall accuracy of the 5 commercial products, and we rank the 5 products by decreasing AUC values. So as I mentioned before, WHO has recommended CAD to replace human in screening and triage setting, not for diagnosis, but only screening and triage. We also think that there are other use case of AI when it's being used alongside with human. For example, CAD can help to work with human to improve their workflow, alert human reader to abnormal images, providing report assistance, quality control, or pre-reading assistance, and etc. There are also 2 products available to procure through the GDF catalog. The first one is CAD for TB. Many of you may have heard about. The version provided through GDF is version 7, the latest version. I will not go into the specific input and output details. I can share the slides after the call because the limited time. I will just mention very quickly the CAD for TB version provided through GDF is slightly different from the previous version. It's actually quite different from the previous version that people have been using from the past. We have seen this version 7 perform much better than previous version, and there's additional such as default threshold score were introduced for the first time. And a data dashboard to manage presumptive TB and link to gene expert or confirmation tests is possible with the newer version. Now, the second product, which is lesser known one, is called infrared DRHS. You can also procure this through GDF. We're offering version 1. To be honest, the input and output requirement is similar for infrared compared to CAD for TB. Perhaps the only differences is that infrared can report on non-TB abnormality, whereas CAD for TB can't. CAD for TB only report on TB. Both infrared and CAD for TB can be deployed with or without internet. And they can be deployed in this hybrid mode, what we call a hybrid mode. Basically, these means is that the CAD analysis is done without internet, but data synchronization and upload can be done whenever there's internet connection. So here's the price of purchasing the 2 AI software through GDF. We're glad to notice that this is the first time we made it possible on the market for AI software to offer perpetual software license for unlimited number of reads and unlimited number of years of use. The only condition is that the software must be installed to or linked to one specific X-ray equipment. Then many of you may have seen this before. So in order to, and I'll get into that later, in order to use the software offline, there will be additional hardware pieces. For CAFR-TB, you would need to use a CAFR-TB box. And for infrared, you will also need to have another piece of device, which is in this case is a laptop. So for people who are interested in using AI offline, please make sure to add the additional software in the procurement. Now, and then there are also service items you can procure, such as installation, training, and support and maintenance. The support and maintenance can be procured up to 5 years, and 5 years is the maximum. Now I want to get into the implementation consideration. The first and foremost, and then this is the question I get asked all the time by country and users, is CAFR-TB compatible with the Fujifilm XR? Is stuff like compatible with infrared? And yes, the answer is for both two hardware and two software provided in GDF catalog, we have tested that. You can pick and choose whichever software and hardware combination you prefer. The exact configuration will, however, depend on the selection of the hardware and software and internet connection. What do I mean by that? So for offline use, when there's no internet, when you want to deploy an X-ray assessment program, and with CAFR-TB, you will need to purchase a CAFR-TB box and use it in your setting. It can be connected with a wire, without wire, to your X-ray console laptop. This X-ray box has CAFR-TB pre-installed. So when this box receives the digital X-ray, it can analyze and generate the results locally and send the CAD results back to the X-ray console. All of these processes will be automated once it's been properly installed. Also for offline use, if you're interested in using infrared, the infrared laptop is required. It functions like the CAFR-TB box, except that this time your CAD result will be displayed on the CAD laptop instead of on the X-ray console laptop. Now, in online use setting, this is not often frequently asked deployment methods because usually strong internet, stable internet is required. But in some cases, stable and strong internet is possible. An online mode is preferred. When a client wants to use Delft Light, the only thing required is that the X-ray laptop is properly linked to whatever CAD cloud, be the infrared or CAFR-TB. This will be done during the installation. Now, for Fujifilm FDR XR for online use is slightly more complicated. Because one additional device with monitoring, such as a laptop or a tablet, is required to go between the X-ray console laptop and the CAD cloud. Because X-ray console provided by Fujifilm has restricted access to third-party software. So this additional device is functioning as receiver of your digital X-ray from Fuji console laptop. Then from this device, a CAD cloud can be accessed through the web browser that produce the CAD result and sent back to the device. There are several implementation considerations involved using ultra-portable X-ray devices. I mentioned portability, and it's a double-edged sword. It's much more portable than their predecessor, but they're still not as portable as what they've been marketed. So please keep in mind the entire system need to be transported to the implementation site, and the entire system can be up to 30 kilograms. And because those devices and components are very delicate, we strongly recommend at least 2 people should be used to transport the device. Then again, still these devices are portable enough so that you don't need to mount them on the truck or on the van. 2 people can carry the package on the motorbike to go to places that are not accessible by a van or a truck. Image quality are being often asked because the output power of these ultra portable X-ray is indeed lower. But keep in mind there is a advancement in the X-ray detector and the console image generation software installed on the console, made it possible still to generate high quality images from using a X-ray generator with a lower output power. We're saying this because we heard testimony from early stage implementer, and some of them are head of radiology, they're head of physicians. The X-ray console laptop, and oftentimes we're seeing that a partner want to use this laptop for multi-purpose, to registering patients, to install other software. But please know that please always double check with the X-ray supplier before you modify the setting of the X-ray laptop. In the case we have seen a partner in country, they want to install a different browser. They want to install Chrome, Fujifilm, without double checking with the Fujifilm. And this has crashed the console laptop and the entire system, and the generators and detector, everything have to be sent back together all to Japan to repair. Now, in terms of power, as electrical appliance, as any electrical appliance, consider your phone. When they're being only used by a built-in battery, the lifetime, the battery capacity can be limited. And the time here, I'm listing in the table, the generator battery of the Fujifilm FDR XR is the most rate limiting factor here, because for the detector, you have 2 replacement battery, but the generator needs to be, unless it's been charged with the portable battery bank, the manufacturer claim on battery itself, the generator can take 100 exposure. But in our early implementation project across the globe, regardless of temperature, humidity, we can never reach 100 exposure. In fact, we're getting to 30 something exposure and the generator is dead. So Delphi Light has a slightly higher battery durability. So about 100 exposure without access to additional battery source. The solar panel, yes, is provided in the full kit, but it's quite heavy. So unless you carry that into the field, and if you really want to use the solar panel with the sunlight to charge it, please keep in mind this solar panel requires sunlight to be directly exposed on the panel in order to really reach a charging speed that is reasonable. The additional hardware pieces for the AI products for offline use, the CAD infrared laptop has a built-in battery that allows for 10 hours of use, but the CAD for TB box doesn't have built-in battery, hence doesn't have battery autonomy. All of this, please keep in mind all these numbers, those are fresh new battery. And I can only, our early project hasn't reached the problem, haven't experienced the problem, but I can only imagine with times of use, the battery capacity will be reduced, and when you plan your implementation in completely off-grid setting, please keep in mind the battery life. Finally, on radiation safety, it's a very important topic as X-ray is ionizing, it does provide ionizing radiation. Currently there is no standardized international policy on the use of these ultra portable X-ray that emit less radiation. But WHO and IAEA, they're currently working on updating the safety recommendation. So at the moment, local regulation, which unfortunately differ from country to country, they are the one to regulate how if you want to use the device in your country and what safety measure should be in place. I'll skip this. Yes, so another important issue when it comes to use AI software, as a previous speaker also mentioned, is data privacy and security. And there's a good reason to be worried about it as well, because these are medical devices and digital tools. Personal information, medical information are being transmitted. We're mindful about this. What we have done is for products that will be offered through the GDF catalog, they will be bounded by the principal agreement that were established between this company and UNOP GDF, so that by default, the ownership of these data will be the country, the program, be you who purchase the AI services. And those AI company cannot use the data. When I say data, I mean any data generated or transmitted. They cannot use the data for anything else other than providing AI reading service, unless a written approval is being provided by the data owner, such as if they want to use your data to do more training, improve their software, and you have not authorized them to do so, they will not be legally allowed to do so. We also provided additional legal support on this matter, because this is so important, by providing two relevant legal template that were drafted by a professional privacy lawyer. The first agreement is data processing agreement. This document governs the legal rights and obligation of party involved in the transfer, storage, and processing of personal data. Another document is a non-disclosure agreement. This document legally binds an individual and organization to secrecy and confidentiality regarding any information shared. By default, in our principal agreement with UNOP, that a client must enter into this agreement with a user or a buyer of CAT services, AI services. So for the interest of time, I'll skip. I'll quickly just mention.
Disculpe que la interrumpa.
Sorry to interrupt you. We're running out of time, and I would like, if you are okay with that, I would like to ask you a couple of questions.
Okay, yeah, sure.
Gracias.
Thank you for your talk. You have presented very, very interesting information, and information that is very important on this topic, and we would like to ask you a couple of questions. The first one is, in COVID, was there a lot of software developed for tomography? Do you know any group that is developing this type of, is working on this type of development for tuberculosis?
So if I get the question correct from the translator, I think you're asking about any of those. Do I know any company that are working on AI for TB also have a products for COVID? And the answer to this question is yes. all the company that I have shown on the product landscape slides. I can pull it out again. Almost all actually have worked on a product for TB using X-ray. The big caveat is that those products for COVID, the accuracy has not been independently assessed, and there has been evidence to show that the X-ray may not be a good tool to screen for COVID, especially in the early stage. Let me just pull out the screen again. And you can access this website, afforhealth.org, to see what are the commercial software available for TB. And again, almost all of them have a product for COVID.
Claro, adelante.
Yes, go ahead.
From my side, I think I just answered the question, unless there's another question.
Por mí.
Sí, muy bien, gracias. Sí, claro. Tenemos otra pregunta.
Yes, very
Dice
good. Of course, we
así,
have another question which says,
puede solicitar acceso a estas tecnologías
in a way that we can
para
request access to these products for research purposes.
And so the question is to access the slides for research purpose. Yes, no problem. In fact, I will even offer, I'll send to the organizer after the call. I'll even offer this resources because it's more comprehensive than the slides. The slides are based on this practical guide to screen TB using ultra portable X-ray and CAD. Again, I will send the link to this the practical guide and to the slides to the organizer after the presentation. Yes, there is actually more in the slides that I have not have time to go over because of some technical glitch in the beginning. Over.
Sí, sí, muy bien, muy amable. Gracias.
Very good, very kind, thank you. I think we can have one more question. Is this equipment support for portable X-rays for use and research on animals?
So these, the X-ray that I have shown, the two X-ray systems that I have shown in the slides, they have been developed and authorized, certified to use in human. They have received marks for human, and the dosage setting. I actually think they're probably not suitable for animal because there's a range of output powers that are different from different product, but I think that might be too high and for animal and also depend on the size of the animal.
Claro, gracias.
Of course, thank you. I think we can go to the last one. What general recommendations could you give for the correct use of artificial intelligence in prevention processes for transmittable disease or communicable diseases like HIV, COVID, and tuberculosis? So AI has many applications in healthcare. What I've been talking about is primarily focusing on chest X-ray. And then we'll only be talking about the diseases that has manifestation on chest X-ray. And I think the previous speaker actually speak more about AI application in a spectrum of diseases using different imaging technology, video technologies, and whatnot.
so I don't think I can really speak about using, at least for computer-aided detection technology for HIV, as imaging tool has not been recommended to use for HIV, COVID. Yeah, it's I think it's important to, maybe one thing overall, it's important to be able to separate the hype from reality. There's a lot of hype with AI, with neural network in the recent years, and a lot of media article reports, 99% accuracy, 98% AUC. And those number, as medical profession, when we read it, we really need to dig deeper on, has the AI been pre-trained on the evaluation set that they use to report on this 99% sensitivity, specificity, and who conducted the evaluation? Is this the company themselves who have clear conflict of interest, or this is an independent evaluation? So separating reality from all the hype is going to be key going forward in medical in medical diagnosis and medical care. Thank you.
Muchas gracias por su respuesta.
Thank you very much for your answer. We really appreciate the time that you shared with us and all this very interesting information about technologies to detect and stop tuberculosis at a global level and also in your country. Thank you very much for being with us. I'm going to continue to close this session. Thank you. Thanks to both speakers today. Thank you for your time. We'll see you soon. We would also like to thank the Study Center and Audiovisual Production Center for support in producing this event, and also the translators into English and the sign language Mexican Sign Language interpreters who have been with us in all 8 sessions of this forum. We would like to remind attendees to record your attendance with the QR code that will be appearing in a few more minutes today, so that we can record your attendance for your certificate. It's only valid for this session. Thank you for attending this second virtual forum on tuberculosis, where we had more than 2,100 attendees from different countries, and including Mexico, Peru, Argentina, Panama, Guatemala, Colombia, the Dominican Republic, Chile, Venezuela, Cuba, Ecuador, United States, and also France, Spain, India, Tanzania, Brazil, and Nepal. And in the case of Mexico, we had attendees from all states, with Oaxaca, Baja California, Sonora, Mexico City, and Chiapas. We're having the most attendees. We have reached the end of this second International Forum on Tuberculosis, and we would like to thank everybody for your attendance and for joining us for these 8 sessions. And we look forward to seeing you at the 3rd edition in 2022. See you then. Bye-bye. Okay, we're done. We're offline. Thank you. Okay, in YouTube, we're off. Okay, thank you. Thank you. We're off. Has Raquel come back? No, I don't think so. Okay, in the English channel, we're still. I'm going to